In this video, we are going to learn about Newton's second law. Okay, so let's go to your notes, week 6. If you look at Newton's second law, okay, it's basically an equation. Yep. Newton's second law can be summarized in an equation. So let me show you how do I do that. So Newton told me in his second law that the net force net force is basically the sum of all forces, okay, and it is equals to mass times acceleration. Okay. The unit of mass is kilogram, the unit of acceleration is meters per second square, and the force is measured in newtons. Okay, now be aware actually, step 1, copy down this equation. Okay, this is your Newton's second law. And yeah, then from the equation, let's have look at the the units. Okay. 1 Newton is basically equals to 1 kilogram, okay, times acceleration of 1 meters per second square. Okay. So if you do the calculation, 1 Newton is basically equal to 1 times 1 kilograms meters per second square. Okay, or 1 kilogram meters per second square. Okay. So just remember this. 1 Newton is equivalent to kilogram meter per second square. Okay. Now the reason, this is the reason that Newton defined Newton. Newton uses Newton as a measurement of force, because otherwise, when we're talking about forces, we have to use a new unit called kilogram meter per second square, which just too much, too confusing. Okay, so he defined force and he made up a unit by his own name, Newton. Okay. Now, yep. Uh, Yep, the other thing is, let me show you an important thing about drawing free diagram with a net force. Okay. Before that, when we drawing free body diagrams, those force diagrams, okay, we we always assumed they are stationary. However, say if I have a dog, okay, dragging this box to the right with a force of 5 Newton, and the friction is say 2 newtons. So when I'm drawing the free body diagram, okay, I need to draw the driving force, okay, which is 5, and I have a friction force, which is 2 or 3. I have a weight force acting on it, mass times acceleration, mass times gravity, okay, and I have a normal force acting upwards. Okay. Now, since this system has a net force of to the right, okay, you also need to draw a direction for net force to the right. Okay, so this is like the second part of your diagram. It is not included in the free body diagram, but you need a second part to show that the net force is going to the right. Okay. Now, yep, we call this kind of diagram a free body diagram, and Yeah, this is a fancy word. Actually, it is just basically a force diagram. Yes. Yep. Now, have a look at this example. So, Ironman is pushing a shopping trolley with 90 newtons for 5 seconds, and the trolley has a mass of 10 kilogram. The friction force is 10 newtons. What's happened to the trolley? Okay. Now, note that okay, note that Ironman pushes the trolley only for 5 seconds. Okay, so let's figure out what's happened during that 5 second first. Okay, so between time, let's write it down this way. Okay, so between 0 seconds and 5 seconds, okay, let's draw step 1. Always draw a free body diagram if you're confused. Okay, so we have a trolley pushed along on the road. So we have a driving force of 90 newtons, and I have a friction of 10 newtons. Okay. The weight force goes down, and we have a normal force goes up. Okay, the trolley is only moved horizontally, so weight force is the same as normal force. So the trolley won't fly this time. Okay, now, and also let's label the net force. Obviously, we have more driving force than the friction, so as a result, the net force will be in this direction. Okay. So using Newton's second law, okay, the net force is basically sum of all forces, okay, which is ma. Okay. So the net force is basically sum of all forces. So let's state this as the positive direction. The direction of net force will be the positive. Always make the direction of net force positive. It's just make your calculation easier. Okay. So I have positive 90 newtons, take away 10 newtons, and that's basically all the horizontal force I have. Okay. Equals to ma. So mass is 10 kilogram, okay, times acceleration. So if I do the calculation, the net force will be 80 newtons, and let's do this. Okay. Let's just write down 80. Okay. The net force is 80 newtons equals 10 times acceleration, which is 10. Okay. The acceleration, do a calculation, acceleration will be 8 meters per second square. Okay, so if I'm going to draw a graph, say if I'm going to draw velocity and time graph of the trolley, okay, let's assume the trolley start at the rest. Okay, for the first 5 seconds, okay, it will have a constant acceleration of 8 meters per second square. So the trolley will become speeding up, speeding up, speeding up until for the first 5 seconds. Yep, clear? So that's first 5 seconds. Now, after 5 seconds, okay, when t is greater than 5 seconds, after 5 seconds, Ironman is not pushing the trolley anymore. Okay. So Ironman is tired or what's happened to him, I have no idea, but he stopped pushing the trolley. So there won't be the 90 Newton driving force is gone. It is gone. If we draw another if we draw another sorry, if we draw another free body diagram, okay, after, so I only have a friction force here, which is 5 newtons. The driving force is gone, and I have my weight, and I have my normal force. Okay, so horizontally speaking, that's 10 newtons. Okay, so horizontally speaking, the only force acting after 5 seconds, okay, the net force acting on the trolley, okay, is going to be the sum of all forces equals to ma, okay, which is minus 10 newtons, the friction force, equals to 10 times acceleration. If you do the calculation, we have 1 minus 1 meters per second square. So afterwards, since Ironman is not pushing the trolley anymore, there will be a friction. There will be a friction. It means, yep, it means the trolley will slowing down. Okay, so if I draw that diagram, okay, after 5 seconds, the trolley is going to be slower and slower and slower, and it's going to be slowing down at a rate of 1 meters per second square, which is a negative acceleration. So if I draw the graph, it will be after 5 seconds, so it will slow down like this. Okay, and I have no idea what's the time. Well, yeah, the graph is not drawn in scale. This should be more, should be less stiff. Okay. Yep. Okay. Now just let's revise what's happened with the velocity time graph. The gradient is always the acceleration. The area under the graph means the displacement traveled. Okay. Say for example, if the question asks you, where well, where is the trolley? Okay. At when time equals to 8 seconds. What you do is you cut the graph. What you can do is you cut the graph and calculate the area under the graph. By the way, you can calculate the velocity by using those constant acceleration equations. So yeah, that's how do we do this. Okay.